Hi guys, it's Dr. Edwards again. I want to talk to you now more about the vector integration, uh, similar to the standard Riemann integration that you learn in basic calculus. But now we're going to extend that whole process to vectors that are a function of some variable, and you can differentiate that vector. You can integrate it as well as shown here. In all cases, though, one has to change the integral to, let me see, you have to reconfigure the integral to get it into a standard Riemann integration form in order to perform the actual integration. Today I'm going to focus on this line integral, and on a later presentation I'm going to focus on the surface integral. Let me see. The surface is right here. So I'm going to focus on this surface integral at some point, okay? Now, the line integral back here. So formally, it indicates that you're going to integrate from some point P1 to point P2. And P2 can be the same as P1. Then it's a circular integral or closed path integral. And so in each case, you have to eventually get the integral in this form or in that form, as I say. And then you further have to configure the integrand as the case may be. Now, I'm going to illustrate this with one of your homework problems, and that's 44 on page 43. And I'm also going to give some comments about problem 43. So here's my rendition then of problem 44. Okay? Learn this problem. Learn how to do it. The author says evaluate, sorry that the E is missing, this integral over the closed path of A dot dr around the closed curve C of figure 2. If A is equal to the variable x minus y for the for the ith component, and x plus j for the x plus y for the jth component. So we want to integrate then in a counterclockwise manner around this closed path. How are you going to do that? You did not necessarily learn that in your basic calculus class. You would have a standard Riemann integral, say, of some function f of x, and you integrated that f of x from some x1 to x2, and you came up with some number. We're going to do a similar situation here, but what I'm going to do, the best approach is to divide the closed path into two portions. That's what I'm going to do. And then express the integral in terms of one variable, either x or y. And then you can perform the integration. All right, let me go on. So in this procedure, dr is equal to dxi plus dyj. So that means a vector A dot dr is equal to the quantity x minus yi plus x plus yj dotted into dxi plus dyj. And then you take the dot product then appropriately, and you come up with this expression that A dot r is equal to the quantity x minus y dx plus the quantity x plus y dy. No problem. Now, one still can't perform this integral because now the integral has to be along that specific path. So, but what I'm going to do is everywhere that I have an x or y, I'm going to substitute for the other. Now, I will choose to favor to substitute for y and perform this integral in terms of x. So that's what I'm going to do. So here I have, so everywhere that, so I will select to write the integrand Let me fix this. So I will favor to write the integrand in terms of x from the path x equals 0 to x equals 1, where along that path y is equal to x squared. And then if you differentiate y equals x squared, you get dy equal to 2x dx. So there I have it. Now I'm going to substitute into this expression that I had earlier. Everywhere that I have a y, I'm going to put in the equivalent value of x. And that's what I do. That's what I do. And so finally then, I get that a dot dr is equal to this expression, which simplifies here. And now then so soon as you get here, you get back to elementary calculus expression. This is a standard Riemann integration in terms of a function of x dx, and you can integrate this with the power law, and you come up with 4/3. So that's the first part of the integral, having integrated along this path from x equals 0 to x equals 1. So we really have come here, but what I did, I favor just moving along the straight line out to where x equals 2, 1. Okay. Now we need to do the second part of the integral. Here now I will select to write the integrand in terms of y. That's just my preference. But one could write it each time in terms of x if you wish. But I chose to write it in terms of y. For the path y from equals 1 to y equals 0. That means that the author has asked you to find the integral in this closed path. So you go out to this point and then you come back along that path. That's the same thing effectively once you make the transition of integrating along y from y equals 1 back to y equals 0. That's what I'm going to do. So here, I make the appropriate substitution, realizing that along that part of the path, I have y squared equals to x. That's the same thing. If I differentiate both sides, 2y dy is the same as dx. So here I start to set up the integrand. I set it up right here, and that's the standard dot product there. Then we come on. I substitute now for dx. And here I've already substituted for x. Substitute for dx, which is 2y dy, and dy stays there. Now I'm able to factor out dy with everything having been transferred to be in terms of the y variable instead of the x variable. I say again, I could have chosen to write this in terms of the x variable and integrate, then come everything favored with dx, but I chose dy. So now I have it to integrate from 1 back to 0 of this functional form, and that's a standard power law integral that we can do. But notice now you must have from 1 to 0, not from 0 to 1, because you're now coming back along the closed path. So when you put 0 into the result of the integration, you get 0 there, and then minus each of these terms here, and there we have it, and there we have it. So we get then that the result of the closed path integral along the second part of the path is a negative 2/3. Then the total integral, represented here along path C, and it's a closed path. I haven't put this circle on the integral symbol. It's 4/3 minus 2/3, which equals to 2/3. That's what I wanted to share with you there. Let me just give a word to you about problem 43 on page 103. That too is a closed path. You can see it is a Scaling's triangle So, and it's a right triangle. So you can integrate along the x-axis for part of the motion, integrate along the y for the other part of it, and then come back along the slant. The only other portion you need to know that on the slant, as you see for this figure, for problem 43, it is a straight line. And if you use the standard equation for a straight line, y equals a x plus b, where a is the slope of the line and b is the y-intercept, you get y equals to 1/2 x. That's the only unknown that's in this problem. So once you get that, and then I put in the value here, I find the slope, and the slope is equal to 1/2, and the y-intercept is 0. Therefore, the equation is y equals to 1/2 x. So knowing that now, I think everyone should be able to do problem 43, as well as representing this problem that I have here for problem 44. Now notice that I have chosen to integrate both problems in a circulatory manner. In a counterclockwise manner. Be aware that on the examination, I may ask you to integrate the problem in a clockwise manner. And so you're not going to get the same answer. You will only get the same answer if A is a conservative force field. And since it's not a conservative force field, integrating clockwise here would be different than integrating counterclockwise, even for the same closed path. All right, I wish you well in this now. So get busy and finish up all of the homework assignments and send them to me. Have a good day.